Most of the programming methods described in this presentation were developed by my controls engineering mentor. This video is an attempt to share my understanding of his system. With this understanding, it is easy to produce code that is reliable, readable, and easily edited. Additionally, these explanations will help with understanding programming regardless of platform or programming language. The two main components of a program are the program variables and the program logic. Regarding variables, we will explore naming conventions and structuring. For logic, we will explore flags, state machines, and action blocks. Variables. Before delving into naming convention, data structuring will be defined. Data structures are groups of variables linked together under a common tag or label. If possible, all variables and tags are contained within a data structure. Structures are necessary for proper organization. The structure contains any data types pertaining to the structure's purpose. This may include arrays, predefined data types, or other user-defined structures. It is best, however, to keep the structures within structures to a minimum. Now on to naming convention. Variable names start with a lowercase single letter used to identify the data type. B for bool, N for integer, G for structure, or S for string. Variable names contain an uppercase three-letter descriptor to identify purpose, function, or process. SYS for system, IDX for index, and so on. Variable names are as short and as precise as possible. G_sysstatus.b fault indicates a system fault status. GIDX_conveyor.t failure indicates a timer failure for the index conveyor. This completes the variable standard overview. Now on to logic. Again, the main components of logic discussed here are flags, state machines, and action blocks. Flags. The actual definition of a flag in computing is a variable used to indicate a particular property of the data in a record. More specifically, a flag is a bit used to communicate a condition or to request an action. System flags, for example, may include flags that indicate the system is ready to start or flags that indicate liquid levels. It's important to recognize when a flag can be used to consolidate logic for other flags. For example, if system OK and liquid level OK are conditions for another flag, simplify instead of rewriting the same logic multiple times. Increasing the quantity of flags increases logic clarity and provides higher resolution processing. Few flags means lower resolution. If scope and terms are well defined using accurately named flags contained within properly grouped structures, the program logic seems to fall into place naturally as if it programs itself. Insufficient flag usage results in messy and hard-to-read code. If you can't write it in structured text, don't write it in ladder. To rectify logical disasters when updating someone else's messy code, replace logic segments with the appropriate flags. Properly describe what each segment seeks to relay. Increase resolution to simplify. Let's look at this example. We find the two logical conditions in this rung elsewhere in flag logic. The two conditions can be consolidated into one. Eliminate excessive branches by simplifying the entire branch into one condition. Repeat for other branches. Once branches are simplified, a single flag can replace the OR gate logic. This process is similar to solving series parallel resistor values for electrical circuit calculations. This is a very well-defined brute force approach. Each chunk of logic is easy to comprehend. Additionally, it is easy to edit conditions without affecting logic elsewhere. Another way to think of this is simplifying connections between points. Cross-referencing fewer connections allows quicker debug and easier comprehension. Now on to action blocks for output control. Action blocks are cell-like structures that operate independently to regulate the control of a single output. The action block is the manager of the electrical output and can refuse to turn that output on if the conditions aren't met. This data structure format standardizes all output logic. The clear flag watches preconditions necessary to run to avoid an error. For example, a cylinder extending into another extended cylinder. The sequence or required flag is acknowledging a request from outside logic to turn the output on. The command controls the actual output based on the mode of operation, conditions required in auto cycle, or conditions required in manual mode. The actual output is on a rung that looks like aliasing to keep it readable. The complete flag lets the requester know the action has been successfully executed. The failure or error flag occurs when the output does not execute properly. For example, a motor auxiliary contact. This error will block the clear flag, and it will notify the alarm manager. To simplify, action blocks consist of prerequisites, control, and results. A single program may contain numerous action blocks. Because they are all in the same format, it is easy for others to learn, to modify, and to troubleshoot. The self-sustaining nature of action blocks lowers the risk of bugs from program sequence revision. Typically, the significant actions are managed by a single state machine. The state machine requests the action and monitors the action block response regarding whether it was able to fulfill the request. Actions are often grouped by an assigned state machine. A state machine is a rigidly structured flowchart written in ladder logic. The first segment updates the state control variable. The subsequent segment contains all of the state elements, which are the components of the analogous flowchart. Only one state is processed at a time. If the state does not equal the first condition in that rung, the state is ignored. A state is in process once the control variable matches the equal condition of the state rung. All conditions must be met before moving on to the next state. When all of the conditions are satisfied, the event is completed. In other words, the detector recognizes the state, then the node verifies or initiates an action, and finally triggers the state transition. A state can write to variables, wait for or read variables, or select the appropriate subsequent state. The following example uses all three types to select which pump motor is to be used. When the flag for pump 1 is true, only the state for pump 1 is processed. After the flag requesting the pump 1 action is set, the pump 2 state rung is bypassed entirely. This flowchart shows how this sequence may be diagrammed outside of ladder logic. In the alternative sequence, if pump 2 is selected for operation, the pump 1 state is then bypassed. Both pump request states are linked to the final state. It should now be clear how the state machine behaves like a brute force flowchart for ladder logic. There are two control variables in a state machine, the current state and the next state. This approach prevents the next state from being executed immediately after the previous state for purposes such as record keeping. To reiterate, the completed state writes to the next state variable. All other states are ignored. The control rung allows a state transition by copying the next state into the current state. State numbers are intentionally large. Each numerical place value provides an opportunity for elaborate methods of organization. For example, states in the 1000s range identify startup tasks, while the 3000s contain a shutdown sequence. The gaps between state numbers make revisions easy. When the sequence requires revision, simply add a state rung in the proper place in that sequence, likely between rungs. Only the state number below the inserted state must change. Record keeping is located in the control rungs for advanced troubleshooting. If the current state is not equal to the most recent recorded state, then a series of copy functions are executed. The first record is selected as the starting point for the copy. A shift array receives the copy, but is offset by 1 to leave room for the new record. The length is set to 1 less than the total record length to eliminate the oldest record. The second copy function takes the current state to be recorded and copies it to the top of the shift array. The shift array is then copied over to the record array at the full array length, and the record is updated. The result of this automaton mimics that of a FIFO, first in, first out, but at the word level. However, the actual process should be viewed as a sort of shuffling. The shift array is necessary because the copy function will not overwrite an array with that same array. This visualization best summarizes the behavior of state machines. One state is processed at a time and will not transition to another state until the next PLC scan. This method allows for recoverability with more advanced control if the state machine is interrupted. Due to the speed of the PLC scan time, the state machine can be configured to check multiple conditions one by one and respond quickly in real time. In reality, this visualization would occur at a much faster rate. Now that we've seen all of the logic components, let's look at them together. This overview will help one see the entire operation. First, the system flags are set. The state machine updates according to those flags. The action blocks respond according to flags from the system and the state machines. The action blocks protect themselves and communicate errors to other automata. If a state machine is inactive, all of its flags reset, including the flags to the action blocks. The key to understanding this system is found in simple mental abstractions. This elaborated visualization shows a more refined mental abstraction. More flags, more state machines, and more action blocks grouped by respective state machines. Like the hardware and software layers beneath it, the program only reads and writes. As above, so below. Contemplating the structure in many different ways, such as diagrams or tables, helps significantly with understanding. This program overview visualization, complete with a state machine controlling other state machines, is my attempt to express how I view the entire system. A program simply controls outputs based on inputs and logic. The inputs come into the system, interact with the flag logic of varying categories, and trickle through state machine logic, alarm managers, and miscellaneous routines to trigger outputs. In reality, programming is programming. The concepts in this presentation are applicable to other program languages and platforms. Moreover, the concepts may apply also to other fields and human endeavors. Program development is a very abstract and technical skill, relying on properly defining scope and terms. Proper software development requires deeper exploration of a broad range of concepts,